maybe you can just close it. You can close the door now, I think. Okay, I think it's time to start for today's lectures. And continuing from the previous lecture, we started about software testing and JUnit testing. And we have a focus on unit testing using JUnit. We had some introduction about what the JUnit is. So continuing from that part, so it's basically a framework, a set of library classes that you can use to test your different components in your Java application. And yeah, if you remember that I demonstrated that how you can use the JUnit in Eclipse. So you can configure your project to use using the build path. So you can add the JUnit using this method. So we have already covered this part. And yeah, we were using, just to give you an example, there is one math class with two methods. One is the multiply, and the other one is for sorting. So, and this multiplication method simply takes two integer values and multiply them in a recursive manner. Of course, you can use a simple or any other kind of method as well. And the sort method takes an integer array and returns a sorted array in ascending order. And then we have a test class. And basically, as I mentioned in the previous lecture, it's a simple Java class. The only difference is that here you use the test class from JUnit framework. And we use a couple of assert statements, annotations, assert, equals. And yeah, and what is important is that we use some annotations in the test class, and we write few test methods. And the basic idea is that in one test method, you should not test more than one or two your methods from your Java classes. So yeah, these annotations tell that this at the rate of test, it's a Java annotation, and it tells the Java compiler that the method which is followed by this annotation is basically a JUnit test method. You can name the method according to any legal identifier, but it's a general convention is that you start your method that you use for testing with a prefix test. It's just a standard convention, but not a limitation or something like a constraint. And we also write our test classes ending with the test, so that we know that these are the testing classes, so not the simple Java classes. And if we look at here, in this first test multiply, this method we have written to test our the mymath.multiply method. And basically this assert equals statements, this takes two parameters or the arguments. The first one is the value that you expect as a result of multiplication. So for example, if we multiply 10 and 0, we expect that the result should be the correct answer that you expect, the correct behavior that you expect from your method that you are testing should be specified as an expected value. And then the other parameter is the actual value that your method is returning over here. And I told you that we get this annotation or these assert equal method from this assert class from JUnit. Basically, if we look at this in the, if we give you an overview of what are the different methods there. So if we look at Java assert, maybe no. Java JUnit assert. Uh, and if you go here, you find a number of different assert equals methods. You have methods defined for, these are the assert array equals method if you want, instead of one single primitive value, if you want to use, if you want to test the value of that are returned as an array, you can use assert array equals method. Otherwise, you can use, there are plenty of assert equals method defined for each primitive type. So we have like 8 different primitive types. So assert equals method have been defined for each of the types, and then we also have assert equals methods for our object types or the reference types of data. So you can, and also other than the assert equal, if you go down, you have also assert false, assert not equal. So you can use these different assert statements to test your methods. So here we have like three different assert statements for the multiply. It's like a simple, extreme cases with the lowest values or the minimum values. And then we have some standard cases like, and also if you notice here, in this assert equal, we only have a primitive types, but you can also specify some meaningful message here. So for example, if a test fails and you want to print out that what is the problem over here. So in this case, for example, if I run this test, it will be more understandable. You can run it. You can run it simple like using this run button from the toolbar, or you can also right-click and select run as JUnit test. So when we run it, so here if you see, we get the output. This is basically the JUnit Explorer thing. And here you see what are the errors, what are the failures, and the runs. So in this case, we have we have run one method, which is like test multiply, and then we also have a test sorting. But we have, since we have commented this line, so this method was not executed. So it means that to execute a test method, having a test annotation is quite important. And but for example, if I just go to this multiplication method and make some changes over here. So instead of having this, let's see if I comment these lines and something like a plus b. I'm intentionally creating an error, so writing a wrong value. So instead of, so now if we go back, let's save this, and if we try to run this once again, you see it says that you have we have run 2 out of 2. So it means that we have run 2 test methods. We run test multiply and we run test sorting. We have problems, the failures in one of those, and it says here, assert equals, and we get the problem over here, and the description you can read down in the downward. So illegal argument exception. So for example, to make it more simpler, if we just comment these lines, and now if I try to run this again, and see, if we go back to this my math, and if I just comment this part again as well, because right now I'm not handling this one. Expected, no, I don't need this one either. So now we don't have an error, instead we have a failure. And what is the failure here? If you see here, the failure, it says expected 0 but was 10. Why it was 10? Because if we go back here, I have changed just the implementation of this multiplication method. So instead of multiplying this method, we suppose this method to do the multiplication function, but actually if you are the developer and you have been writing a code since early morning, and if you're writing maybe your code late night and you're tired enough, so you can make this kind of mistakes. So and then but if you are testing your code, if you have any problem in your implementation, your the JUnit test will help you to identify those codes. Okay, and this is not only in this case. So from this you can understand that yeah, the value which was expected was, because if we multiply 0 with the 10, the expected value should be 0 and not 10. But since our this method is doing addition instead of multiplication, so it returns the value 10. But now if I go back here and if I just, instead of multiplication addition, if I use 10, and if we run this thing once again, so in this case we have no problems here. Okay. And also another thing is, so for example, maybe someone can open the door. Yeah. Another thing is when we use this plus addition thing here, and when we run it, we have this error in the 0 but was 10. So of course you can understand this, but if you want to make it more meaningful, there is another form of this assert equals, where you can pass the string argument or the parameter to specify the method, what should be actually the meaningful method. So we can we can write here like 10 and multiplied by 0 should give yeah, equal to, or must be, yeah, something like that. 10 multiplied 0 must be 0. Okay. So if we now run this thing again, yeah, now if you see with your yeah, the failure thing, you can read this whatever you have written over here, the description of the failure will be printed over here. So get you just to give you more information, so you can use it. It's up to you. If you want to use a simple form of the assert equal, you can do that, or if you want to provide more information to the developers, or for the home you are doing the testing, you can use the print methods within the equals. Okay, so that's basically how you can use yeah, I mean different kind of test. So that's the simple, yeah, the multiplication method over here. So if we just quick go through this, and then we have this yeah, my math test class, which we have this testing method, and then we have several different test cases. Okay, so we test with the smaller or the minimum values. We test also the standard cases, and then we also do some test on large values or the extreme values. And then yeah, that's some description about the test.java, but I think I have already described all these things. So we need to import. First of the thing is that which is important is that you need to import the org.junit.test class, and then you also need to, if you are using the assert equals or assert not equals, assert same, these kind of different assert statements, then you also need to import this junit.assert yeah, class. And yeah, and what else is important, that yeah, that you can use a number of as many as assert equal statements in your class. So and then we have another this method, sort method, and basically it's using it's implementing a selection sort to sort an integer array, and we can also test this method. So if we look at back over here, so we have this method down, test sorting, and here we have few cases. In this case, we are just testing it with an empty array. So and we use, since if the array is an empty, its length must be 0. So we test it using this statement, and then we test with only one element in the array, and then we have tested it for more than one element. But since just to test that we have like 3 elements, and then here we test assert equal 3, since the array length, this is the expected value and this is the actual value over here. And then we have a for each loop just to see that all the elements are returned by the array are same or not. And then we also used the sort method here. In this case, since all the elements are same, so there will be no actual sorting here. But in this case, we have elements in the reverse order, so in descending order, but we want to sort it in descending order. So, and then it means if the array is sorted, then 1 should be at the index 0, and 3 should be at the 4 should be at the last index, which is index 3. Okay. So these are the different. So my recommendation is that you already got this the code for all these example on the Moodle page. So just go through it and play with the different tests and see how you can use these testing classes and testing features in your own implementation. So here we have plenty of other asserts other than assert equal. You can use also to check the binary values, so whether the method returns true or false, and if a method returns a null or not null. So you can also, because sometimes you have this method returning a null values, and we have the equal method checks the values, and if you want to check the references, the reference variable, and if you want to see that whether the two variables are pointing to the same reference variable or not, in that case you can use assert same. And assert array equals, as I told you earlier, it's when you want to check that whether the the arrays are equals or not. We have another example. It's a kind of a bit larger than the simple math multiply. So we have, we have another package over here. We have in which we have an interface int list, in which we are basically implementing a list of integers. So it has like add, remove, get, and various methods defined. And then we have a class list implementation, which is implementing this integer list. And if we want to test these different methods like add, remove, get, size, and index of, so to test these methods, we have similar to the earlier test class. So we have, if you see over here again, we have the similar. We have imported, in this case maybe, org, and then we have yes. So, and then if you look at here, we have another annotation here instead of so far we looked at the rate of test annotation, but if you want that some of the methods should be run before every test method runs, so there are a few other annotations. So this before annotation, it's if you mark a method with a before annotation, then the following method with which you have annotated the before, that will be executed before every test method. So for example, if you want to do some initialization of the variable that you use, for example, if you want to initialize the fixture data, the input data, so you can use this setup method and together with this before annotation. And we also have after annotation. After the methods that are marked with after annotation, those that are marked with before, they will be executed before every test method, and those who are marked with after, they will be executed after your every test method. So for example, here I just simply printed a message that going to run test plus test count. So this test count will actually counting the number of tests that you have performed, and then you have this done with test count. So, and then your actual test methods are down here. In this first test init size, we are just testing the size of an empty integer list. So we have created an integer list with the name of list, but we have not added any elements. So if we have not added any elements, it means the size of the list should be 0. So that's, and we can assure this, we can check this using this statement. And then we have, if you want to test your add and get methods, so we have another test methods here. And I use this build method just to create, this is my private inner method, just to create a list of some size. So if you want to create a size, list of size 10 or 100, you can use this method and pass the size as an input parameter, and as a result you will get this int list type as a return. And if you look at this method, it's basically using a for loop, and So it means starting from the 0 and then until the size. So it means that the list will contain the elements starting from 0 until the size. So if you have a size 10, then the elements will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 until 9. Okay, so it's like just starting from the 0 and then ascending, incrementing by one value. And if we go back to this add get, so here I say that build a list of size 5. So it means since the size is 5, then the list size should return 5. And then we have another list where we have size 10. So basically I'm using two lists, list 1 and list 2. One is size 5, another is size 10. And then but when you are using this build method, actually you are testing your within this one, since you are using this add method. So when you use this method, you will automatically get testing for the add method. And then just to, so we get the testing for the add method using this build. But if you want to test your get method, we have some tests defined for this get method over here. For example, in this case, if we have like this, if we want to set, if you look at this for loop over here, so we are running this for loop from index I0 and then list2.size, and we know that in this list we have elements initialized from 0 until the size, so the values will be the same, and we use this assert equals to test whether the get method returns correct values or not. And we also have used since if you go back to your get method in your implementation here, you see that we provided an index and we expect this method to return a value which is stored at that index. And before that, we want to validate whether the index is correct or not. So we have another check index method. So for example, your index should be within 0 and size that you have specified. For example, if a user specifies size -2, which is an invalid index, so that in that case it should throw index out of bound exception. Or if, for example, if you have a list of size 10, but if your user wants to specify to access an element at index 15 or more than the size, then it should throw index out of bound exception. So, and you can test whether your method throws an exception or not by using the try catch statement. So we use a Boolean variable, and initially it's false, but then we use try block, and we try to list one.get -12. So -12, you obviously know that it's invalid index. So in that case, it should your method implementation should throw this exception, and it means that catch block will be executed, and we catch this exception and just change the value of result to show. So to find out, just to indicate that whenever there is an exception thrown, the Boolean variable is set to true, and then we just use the assert true, and we provided the value of. So in this case, since the value will have been true, so this will be tested. Okay. So these are the different ways that you can use your testing, test methods. And as I told you before, you can use the before and after annotations to do some tasks that you want to do before or after the execution of each methods. Yeah, that's just a simple description of what we have done in that class. So what happens basically when we run JUnit test class? So other than the before, we also have another annotation, which is a before class annotation. Before annotation is used if you want to execute a method before the execution of your each test method. But then sometimes we want to use to execute a method not before every test method, but only once when your class the test class or the test class has been executed. So if you want to run a method only once before the test execution, we use this before class, and similarly we have an after class. But if you want a method to execute each before every your test method, then you should simply use the before and after annotation. So in that case, so for example, if we go back here, we don't have any in this in our test. We don't have any before class. So if you run this one, You only will get the methods that are going to run before the test one. But on the other hand, if you have before class, we will look at before class method in a short while. Then this method will be executed before every of your class execution. So here is just a demo class. So maybe we can go again to this JUnit demo. So here we have simple. We're not doing anything fancy over here. Before class, and you can name these methods whatever you want. This is just so one-time setup means like this method will be executed only once because it's a before class annotated with before class. Okay, and then after class similar to the before class. So for example, if you want to initialize or if you want to open, for example, if you're reading from some file or input stream, so before execution of your test methods, you want to open the connection with the file or the input stream. So you can use the before class method and initialize your resources over here. And if you want to use close your resources when the test method execution has completed, then you can use this after class method. So in this case, if you look at here, we have 3 different test methods. How we know? Because from this @test annotation, we have 3 test methods here, and then we have this before, after, and before class and after class method. So can someone tell me how many times this before class and after class method will be executed? 3 times. Why?
Before every method.
No.
Before every test.
Yeah, no, not before class and after class. They doesn't execute before every test method. Before, yes. So they will only one time. Okay. But how about these 2 methods, before and after? How many times? They will be executed 3 times. Okay. So that's the difference basically between before class and after class and before and after. So just to give you an overview, if you just simply run it here. Yeah, before class, which is a one-time setup. But then if you see this before, it is executed before every method. Before setup, before setup, before setup, yeah. So coming back to the annotations, so we already have seen this, basically the annotations are, you can say that these are metadata, or the tags that are used to provide some specific instructions to your compiler or other tools that you use. We have several different annotations. We have this @override if you want to override a method from the parent class in your child class. So you can use @override, and sometimes you know that if you're using, for example, a deprecated method, then Java compiler normally throws, it's not an error, but it will throw warnings. So if you want to ignore those warnings, you can use this @plus warning annotation, and we use this @test annotation. Is used by the JUnit. And then since you are nowadays writing some JUnit test for your assignment too, so there are a few suggestions that whenever you implement a method, it's a good approach or recommended approach is that after implementing a method, you should write a test and you should test that method. And don't do exhaustive testing, maybe only in a one test, just 1 or 2 methods, not more than that. And and focus on standard cases or extreme cases, and don't go like very exhaustive testing, because if you spend too much time, and it's also you cannot even guarantee that you have covered all the possible scenarios, because there could be, depending on the number of users, there could be a number of many possible, maybe thousands or more than thousands different scenarios in which and the input combination in which a method can be used. Okay, so here are some readings. So I hope you have already looked at, so you can go through this. And then, as mentioned here, that in the next lecture, which was today, we were supposed to cover this data structures part. So from onward, we will continue with today's lecture. which is about data structures and the different implementation methods used to implement the data structures. Can someone just briefly describe what a data structure is? Anyone? Yep. That holds multiple values. Yeah. How do you differentiate between data structure and a collection? We already have studied collections. Yeah. Yes. Yep. Queue, stack. Yeah. So basically, as you said, that it's correct that the data structure is kind of a model that we use to store or handle related set of data. So basically, the collections we have already studied, these are the Java implementations of different data structures. So Java already provides us APIs or library classes in the form of Java collection framework. But in this lecture, other than the use of those collection classes, we will learn how we can define our own data structures. If you want to, for example, if you have a kind of a data that cannot be, or you have some kind of operations that are not supported by Java library classes or the Java, the data structure classes provided by Java. So you can, in that case, you can create your own data structure. So how you, and we will learn about how we can define our own data structures and use them for our own problems. So as specified here, it's we often, I mean, when you are writing a program, of course, you are handling different kinds of data. For example, if you are implementing some system for a university or a college, so you might possibly you are dealing with the data about students, courses, exams, and if it's if you are doing some research and conducting some experiments, so you often have data collected from the experiments. So you might have a number of different kinds of data, and also another thing with the data is, I mean, one thing is the values of those data, and then you also have operations that you can perform on those data. So if we look at here, it's basically each of the data structure is defined by a name, and other than the name, what we have is the type of the data. So what kind of data could be there in a data structure? It could be an integer, string, numeric, or maybe a user-defined type. And then we can also, we'll have a number of different operations. So maybe addition, multiplication, or percentage, or whatever different kind of operation that we can, sorting, searching, and add, remove. So what kind of different operation that can be performed. An example of a data structure is, for example, if we have this string stack. In this case, maybe we can look at here. If you go back. So normally, we define data structures in Java using interface definitions and some documentation comments. So if we talk about this data structure definition, so in this case, this string stack, it is the name of the data structure, and then the values that can be stored and returned by the different methods of this that are stored in this data structure are of type string. So in this case, if you go back here, so the name is string stack, and the different data types, sorry, not different, but only data type that can be stored in this string stack type of data structure is of type string. And then we have defined the operations are, if you look at here, we have these push, pop, pick, size, and empty. These are the different operations. Okay. And we also have, I mean, some other, if we look at commonly used data structures, I think we already have looked at them in the lectures about collections. So we can have a list, which is a list of elements, and we could have a queue. Queue is also a data structure in which we have like first in, first out kind of structure. So stack, we have a last in, first out. And we can have a dequeue, and the difference between queue and dequeue is that in a queue you can only add or remove elements at specific sites, not only on one specific side, but in the do queue, you can add, remove on both ends, both at the front and both also if you want to remove or add at the end, that's also possible. And we have a set data structure that doesn't allow to have duplicate values, but it's a non-ordered collection. We have a map, tree, and a graph. So we already have looked about most of them, and we also have looked a bit about tree, but we have not yet talked about graphs. So in today's lecture, we will study something about the list, and then we will also study more details about the tree. And in the follow-up lecture, we will talk about more about graphs and how we can define our own graph-based data structures. So first of all, we have the simple data structures, which are the sequential data structures. And what does the sequential mean? That in these data structures, we have elements stored in a sequence, and each element has a position which is known as an index position. And the simple sequential data structures we have are stack and queue. And if you look at the stack, it's like last in, first out. So, for example, we have, if these are the elements, so we can add or remove the elements from the stack only at the top or at the one end. But if you look at about the queue, the queue, it's like a queue at maybe at the airport or some shopping store, where the customer that has come first will be served first. So if you come late, then you have to wait in the queue. And the same is here. So we have a queue, and here is the guy who is at the first, and he will be served or dequeued, accessed at first. And the one who comes late, he will be queued or added in the bottom or at the last end. So, however, these stack and queue, they are very simple to use, and also they have a very limited operation. So they don't usually support searching and this kind of operations. So we normally use just to add and remove. If you want, if you have a kind of if you have a program that requires only storage of data, and you can add and remove data, then you can use stack and queue. But if you have something like a sorting, if you want to perform a sorting, and then maybe you have to look for some other data structures. And then the DQ, it's a modified form of the queue. The difference here is that you can add and remove at both ends, in the front and at the back end. And then we have a list. The difference between list and other three are that in the queue and stack, we can add and remove at specific, either at the front or at the bottom or the back end. But in list, you can add, remove at any index. You can remove, you can get from the front, you can get from the end, or maybe you can get or remove elements from the middle or any position. So in the list, basically, we can access elements at any position. Okay, so that's the string stack interface that we have already looked at in Eclipse. And as it says that if you want to implement your own data structures in Java, we can do that by defining an interfaces. And we have studied the interfaces already. How can we define an interface? We can do it like using interface keyword, and it is similar to class definition. But the difference is here we have only the abstract methods, no implementation here. And this string stack data structure, it specifies that it will have these operations. The operations are specified by defining the abstract methods. And the name is specified over here, and the data type is specified. It's basically the values that you can store and retrieve from this data structure. Okay, and we can use different data types in a data structure. We can have a fixed type. For example, this string stack data structure, it has a fixed type, which is of type string. You cannot use it for other data types, for example, Boolean or a character or integer. But and you can also have a data type of object and object class, which we know that it's a parent class of all Java classes. So which means that we can use if you want to store any types, we can use, if the type of a data structure is object, it can store any type of values. However, the problem with it that you need to typecast every time when you are using this value. And the more better solution is that we can have a generic type. And we have learned that how can we define generic types in the lecture about Java generics, and where you can specify the type parameters and you can define the parameterized data structures. And in this case, the data type is of a data structure will be dynamic, and it will be decided whenever you create a new instance of that data structure. For example, we have an array list which is of type generic, and if you want to use a list of strings, here we have this string type argument. So in that case, it will become of type string. But if you want to use an array list, if you want to create an array list of doubles or integers, so you can replace this string with whatever value you want, and then it will be of the type that you wanted or you are looking for. Okay, yeah, so as I said before, that it's not recommended that you should have a fixed data type in your data structures. Why? Because it's obvious that you cannot reuse that data structure for other types, because if you have defined it for Boolean or character type, then you can use it only for that specific type. You cannot use it for integer or strings. And the better if you are defining your own object is to make it of a generic type, because then you can use it for different data types, and you can decide that when you are creating your instance of that data structure. And some common implementation techniques. The data structures could be implemented in a different ways. So we can have, basically we have an array as a basic data structure that can be used to store or group the values. So we can use arrays features from the Java to implement our own data structures, or we can create linked type of data structures where we what does the linked means? We will learn more details, but briefly you can see that in the linked data structures we have multiple data structures which are connected to each other, which have some kind of. So I know one person, and then one person knows another person. So we have a kind of linked associations, and and then we can also have a few other forms like tree and graphs. And it's important that this kind of different techniques that you can use, they have some pros and cons, so they can affect your performance of your application, so how efficient it is. And so while, I mean, the simple way is to use an array-based, but array-based implementations have some problems, because if you're using the array-based implementation, then you have you have to specify the size, and you will have a problem with the resizing, because if an array becomes full, then and if you want to add more elements, then you have to resize the array. But on the other hand, if you have a linked list type of implementation, that will grow and shrink dynamically. And it's also sometimes the array-based implementation lead to memory waste of memory, because if you have created an initial array-based data structure with size maybe 500, but you have added only values like 10 or 20, then the additional memory allocated to that array-based structure will be no use. Okay, and just to look at to create, we have this example int list, and which is simply as we seen in earlier lecture, we have about this testing JUnit test, where we have this interface int list, which extends iterable interface. The iterable interface we have already learned about in Java collection. So it's basically each Java collection data structure implements this iterable interface, and this iterable interface has only one iterator method, and that method returns an iterator object. And the objective of that iterator object is that we can use the iterator object to visit the different values in that collection. So if you, for example, your for each loop, normally you need to define a for loop if you want to visit or access different values in a collection. But if you have an iterator, you can use the iterator methods and you can have your own implementation of the iterator. So we have this list of integers with the several methods: add, and then we have add at. This add method simply add a value, yeah, in the last or in the front. But if you want to add at some specific position, then you can use add at. This takes a value and also takes an index position. So for example, if you have a list of 10 values and you want to add an element at index 5 or 4, we can use this method. And then we have a get and remove. So and as I talked about, we can implement this interlist method, interface or data structure, either using an array, or we can also implement it using linked list based implementation. So at first we look at how we can do this using an array. So as we know that the interface is simply a definition of an object method. There is no implementation in here. So in order to have a concrete implementation of this interface or data structure, we need to implement it. And the implementation class is here. We name it simply array interlist, which implement this interlist method. And as we know that this is going to be the data type of this will be an integer. So we have an integer array of which we name values, because we know that we are going to store the values. And initially the size is equal to 0. So but when we create the array interlist, when we instantiate in the constructor, we have initialized the size to be 8 or 10 or whatever you want to do it. And then we have an add method. And if you look at here, this takes a value and adds the value over here. If the size becomes full, equal to the values dot length, and if the values inside this array becomes equal to the size, then we need to resize it. And we do it resize means that if you go in the resize method, we create another array with the name of temp, and we double the size from the previous array size, and then we copy the values from the earlier array into this temporary array, and then we reference this temporary array to the actual values array. Okay, so you can also look at this. If we go in here, we have this interlist interface, and some detailed comments over here, and you can see what methods are here. We have a size, add, get, index, some documentation details over there as well. And if we go here, we have this array interlist, which is of type values. And so we have an add, which is just adding elements at the end, and we have an add at, and before and we, as I told you earlier, that you use add at method if you want to add values at some specific location, and or the index. And before adding these values, we check whether the index specified is a legal index or not. And for this, we have another method, check index. So, and if the index value is not correct or valid, then it should throw index out of bound exception. You can see this here. Okay, so and also if the size becomes if the array becomes full, then we need to resize the array. So these are some kind of problems here as in the array based implementation. And here we have also another problem with the array based implementation is that for example, if we have a maybe I just need to switch the camera view for the board. Yeah, here. So if we have these values, index 0, 1, 2, 3, 4, 5 values, and we have some values like 2, 4, 6, 8, 10, 12. And now we have this C over here, and maybe one more. If we use this the method add at, no, we don't have it here. but we have it in the implementation. So if we call this add at method, like yeah, add at, and the first parameter is the value. So the value, let's say we have a value equal to 20, and the position we want is index 3. So, but since it already contains the value, to add a new value at this position, we need to move all these elements to the one step to the right, okay? So 8, 10, 12, and then we can have 20 here. And the same will be if you use this remove method, and if now I say remove element at index 3, in that case, if I remove this method, this value at this index, then I have to move all these values to the left, okay? So it means that if you have a frequent add, and remove operations, then this kind of implementation will be not very optimal, because every time you add a value, you have to perform also these shift elements or the shift values, and also when you remove the values, you have to perform this kind of unnecessary shift or the shifting of the values, okay? So for example, when we are here, if you see here, remove, at first we check the index, whether it is a valid index or not, and then we start from the index, which we have specified, and we go until the size, and here we shift the values one step to the back. So if you see here, we have the I is from the starting index. So for example, in this case, if we say index 3, if we say the index is 3, so here in this variable the value is 3, and we use this I is equal to index, initialize I with the index. So in this case the value of I will be 3, okay? So and then the loop condition is, so in this it means the I becomes 3, and then we have the loop which should run until the size of the array, and the size in this case is yeah, so it's like size is equal to 7, and then and here what we do, we say that value I should be equal to values I plus 1, because why? Because we want this index I plus 1, this value to move here, and this value to get this value to move here, we have yeah, we need to do I plus 1, because one index after the value that we want to remove should be moved to the left, okay? So coming back here, so that's why this means that if you have so many add at and remove operations, then you have to, a lot of yeah, the performance of your implementation will not be good. Yes?
I have a question regarding this
The previous one, yeah.
Here, if we going to backward,
Yeah.
backward, at the end we have one space here at the end of the array.
Basically, I mean, yeah, the space will not be removed. It will be only the elements that are removed, because it's an array-based implementation. So if you have created an array of size 8 or 10 in the beginning, so in the memory you have already reserved a space equal to the size of the array. Only the values will be removed, but the memory space will still be occupied. Okay. Now carry on.
Yeah.
Okay.
Sorry.
Yeah.
Question.
Yes.
Size will be minus.
Size will be
Minus.
no.
1.
Why?
Since we removed one element from the.
No, that's the problem, because in the array-based implementation, when you add the values, you need to take care of the size by yourself, okay? And when you remove the values, in the memory, the size will remain the same. It's only the number of elements that will be added or removed.
I mean the
elements, yes. Yeah. That will be plus or minus. So when you add, the size will be incremented by 1. When you remove, the size will be decremented by 1. Okay. And here we have this iterators and iterable, and I think I already explained you. If you for the data structures, because we often have to visit the different elements in that data structure, no matter if it's a list or if it's a stack or a queue or some other kind of data structure. And the Java provides us with this iterable interface. And as the name, the iterable indicates, if a class or a data structure is implementing this iterable, it means that that element or that data structure can be visited or iterated using this the iterator interface. Because why this can be done? Because if you go into the definition of this iterable interface, there is only one method defined, which is an iterator method. And if you look at this iterator return type of this iterator method, it returns you an object of type iterator. And when you go in the iterator interface, you have this has next and remove methods, operations defined. And you have often seen in your Java code that you have been using this has next and next methods. And these methods are used to visit or iterate your different elements in a data structure or in a collection. So, and usually all those the classes that implement this iterable interface can be iterated or visited in two ways. The one way is that we use iterators. How can we use the iterator? For example, we have this array list type, and when we call this list.iterator method, it gives us an iterator object it, and then we have a while loop. In the while loop, we have a condition it.hasNext. It means this the next hasNext will return true if you have more elements in the collection. Otherwise, it will return false. So, and the other way is that you can use the for each loop, which is a modified form of a for loop. But however, to work this for loop for both of these methods, it's important that it's required that the data structure or your collection should be implementing the iterable interface. Otherwise, you will not be able to use any of these two different options. So basically, it's if you go in the back end of this for each loop, the for each loop is using the iterator method approach as well. So it's more like a syntactic sugar where you have something, the complexity has been hidden at the back end. So, but the for each loop also uses this this iterator way. Yes.
I have one question.
Yep.
We are using the iterator and for loop.
Yep.
Both are same, means we are
You can use any one of them.
substitute or
Yeah, these are the substitutes. No, these are the substitutes. You can use any of these two approaches.
okay, means there is no difference.
No, I mean in the output there will be no difference.
Okay, means iterator will scan all the elements of the array.
Yeah. Yes. Exactly.
As we are scanning with the for loop,
Yes.
and we initialize and we tell the for loop that it should iterate through
Yeah.
the
So from here, basically, if you read the syntax, I mean, this should be read like for each, because that's why we call it a for each loop. For each integer j, okay, in this colon is, I mean, it's normally we call it a colon, but if we are talking about a for each loop in Java, then we say it's as an in. For each integer j in list, whatever list you have specified over here. So it will go and automatically, but in the backend it's using the same iterator method. So basically you can use any of these two options. This one is seems to look more simple, because here you have only written these things. You don't need to specify and then use the next method. So you can simply use and print the values through this integer j type. Understand? Okay. Yes.
Isn't iterator provides a copy of the array list rather than the real?
What do you mean by copy of array?
Like if you will have iterator and you will do some operation, you're not doing it in the real one, rather you get a copy of it.
Yeah.
But if you will do on the for each loop, then you're really changing the element. I'm not sure.
Mm,
I read this, there is provides a copy.
I'm not sure about that, but we can look at this. So if you want, we can check it. But I think that if they both are the same in behavior, so then it should be the same thing. But I can check this one. Okay. And yeah, and we can implement these iterators. So if you go this over here, so we have yeah, you have this iterator method, and which is returning this object of list iterator, which is an inner class here. And if you see this inner class, it basically implements this as next and all the other methods of the iterator class. So, and the reason why we use this iterator is simply that they are easy to iterate. You implement this as next and next methods, and give access to data without chances to modify. Yeah. I think I got an answer for your question here, because it says that you should not be allowed to modify the data, but I will double check these things. Okay, so next we will look at the next part. We will have a linked based implementation. So instead of array based implementation, another option is that you can use linked list based mechanism to yeah, to implement your data structures. But I think before that, maybe 5 minutes break just to stretch your legs. Okay, so see you after 5 minutes, not 10 minutes, because I want to finish this lecture and not hang on in the next lecture. Okay.
Hi.
Hi.
Sir, can we use more than one interface class?
Yes.
比我看的今天就还有点快，不知道怎么改。去年就自从我上车之后，后来后面长时间长的，今年差9亿，最后还是那个。所以第二题写的挺那个。
Okay. Okay, yeah, I think 5 minutes are over, so sorry to disturb you in the middle. The next part, we will look at about the linked list based implementation of data structures. And the first thing maybe that comes to mind is like why we need a linked list. It's basically we use this kind of implementation due to the problem with the array-based implementation, which we already mentioned when we are talking about the array parts. The problem is with the add, at, and remove methods. So whenever you add a new element or remove an element, you have to readjust the different elements, because when you add, you basically especially add at a specific index, you are increasing the element, and then you have to shift elements. And it's also the possible that if you are not using the array to its full size, then you are wasting the memory. So the better solution is instead of using a fixed size array, we may have a linked list. And the linked list, if you look at the structure over here at the bottom, we basically have multiple nodes, and the list is basically the set of n possible nodes, and the n means maybe in the beginning you don't have any value, and if you have a list empty, then you have no nodes. So these nodes can be 0 or more than 0, and so it means that basically to implement a data structure using a linked list, we need two classes usually. One is this to have a general starting point of the list, and then we have a node class which maintains the values or the data. And in this node class, we also have a pointer to the next node. Okay, so basically this node, each node will have two attributes. One will be the value, and other will be the address to the next node. And what will be here? The list. Basically, the list will have two attributes as well. The first attribute will be the head, and head will be the pointing to the head will have an address of the first node in your linked list. And then we also, if you want to maintain information about the size of the list, so you can have another attribute, size, which keeps the information about the size. So whenever, it means that whenever, right now we have 4 nodes here, and the head points to the first node, which are and if we say that's node 1, and this node have a pointer which is pointing to the next, and the next is so on. In this way, we have we have defined we have connected the nodes with each other, and this connection of nodes basically is since they are each of them are linked with each other, so that's why we call it a linked list. And yeah, and if you have a head, value, and next, which we already have described. So the head is the address to the first node, and the value is the value of the data, and the next points to the next node in the list. Okay, and if you look at, and if we compare this, if you go back here, so basically if we just see If we have here int list, and then to the other side, if we just see how the linked int list looks like, yeah, no. So basically, if you see here, both are implementing the int list interface, since we want to have an implementation for our same data structure. However, this here we have a integer array-based implementation, values of type which are stored as an integer. But here we don't have anything like values or array of values. However, we have a field attribute and field size. And if you see it here, in the add method, the first time the head is pointing to a null, because when you in the beginning the list will be empty, so the head will not be pointing to any address. And if the head is not pointing to any address, it means that if it's pointing to the null reference, then it means the list is empty. So, and when we are adding the first element, we check the head, and if its head is equal to null, it means that the list is empty. So we create a new node. And if we look at new node, what is new node? Basically, it's an inner class. If we go down, private class node, and this private class node is actually a representation of this part here. And if you see here, we have only two attributes, next and value. So, and if you see in this class, we have also two attributes, integer value and node next. Okay, and then we have a constructor which is just allocating the value that you pass when you create a node type object to the value object. And so if you add a first element, we check whether the head is pointing to null. It means that the list is empty, and in that case we create a new node and assign the address of this new node here. So for example, if we have this some elements like 5, 10, 15, these are the values, and if we want to store in these values to this linked list, in the beginning, head size is equal to 0. When the size is equal to 0, the head will be pointing to the value null. But then if you want to add this value, we can add the values using this add method, and we call the add method add 5. So, and we go here, we check if head is equal to null. Yeah, that's true. Head is exactly equal to null. What we do, we create a new node. So it means that we create a new node, and if you see down there, this is the inner class node which has two attributes. One is the value, and another one is another attribute, a node type, which is also equal to null. So in this means we have a value, and then we have a next. So when we create a new node, and the value that you want, that you passed as an input parameter, is passed to this node type constructor, and through this node type constructor, this value is assigned to this value attribute. So it means this value from here will be assigned to this value 5, and next will become, since we don't have in the constructor, we don't have anything for the next, so the next will remain as null. And then, so from this we will create this node, and after creating this node, we are passing the address, the reference of this node, to the head. So it means now this head will have an address to this, and this will be null. In this case, we have added one node to an empty list. Next time when we call this with the next value, let's say 10, we go here. Now we check head exactly equal to null. No. Now the head will have the address of this. I don't know what will be the address. Let's say this is the address. So then in that case, we will go to the else part. In the else part, we create a node type reference node. See, this is only a reference. This is not like we are not creating new object yet. And we give the address, this address, to this variable, like by saying like head. And then we see that while node.next. Basically, we are using, because this 5 should be inserted after this node. We want to, the new node is going to add it at the end. So that's why we use a while loop to find the end of the linked list. So this while node.next not is equal to null. So starting from the first node, because now this node is pointing to the head, we go to the next value, and the next value is equal to null. So after visiting the first value, we will get the last element, which is the node is equal to node.next. And after getting this last element, node.next, so in this case, when we iterate this while loop, starting from the head and then going through the next, until we don't get this null like the last element, we keep on iterating. And once we got the last element, in this case over here, we create a new object, new node. Again, like a value, and specify the value here. And since we have not, we use the same, the next will become null here. And we pass this new node to the node.next. And in this case, this node.next will be connected over here. Okay? So in this way, you will keep on adding new elements. And every time you add a new element, in the end, you increment the size variable. And similarly, we can use the get method and specify the index, and to get the element at a specific location. However, before getting the that element, we check index, similar to the array-based implementation. And if the index is not a legal value, it should throw an exception. But then after that, to get to the specific index, remember the thing is the same. We start from the first element and we say that the index of the first node is equal to 0. And then we have integer I is equal to 0 and I is less than equal to index, because we want to go until that element only, not after that. And we keep on node is equal to node.next. So it means that we're starting from the head element here, and we go to the element that we want until the index. And so when you run this loop, you will get the node that you want to access, and if we return the value, because we don't want to have the full node. We want this get method to return the value that has been stored at that node. So these are the simple operations, but the way of indexing or accessing the value is a bit different. Next, what is important here, or important to understand here, is how the add method works in a linked list. So for example, we have, forget about this part, we have this list with these 4 elements here. The first node has an element 5, 2, 8, and 6. And it means the index of this value is 0. This one has a node is index 1, 2, 3. So for example, now if I want to add a new element at index 1 in between 0 and 1, so how can we do that? Let's see. We use this add at method, and index in this case will be having a value of, let me clean this thing. So let's say we call a method add at with the value 9 and index is equal to 1. We go here, we created a new node and assign the value. So it means that this is a new node, value is equal to 9 and next will be null because we have not done anything yet. New. If index is equal to 0, okay, it means that if you want to have the element at the start of this point, because this is the 0 in position, that's the simple case. In this case, we only need to point the head to this new node that we have created. So what we do is, but before that, before assigning the head, we also need to preserve the value of head. So we forward the nw dot next to a head. What it means that now this new element will be pointing to the what earlier the head was pointing, and then by doing this new element will have address to the this already having earlier element, and then we simply point the head to the new value. However, if it's not, index is not equal to 0, because in this case it's a 1, index is 1, so this condition will be false. We go to the else part, and in the else part we need to find out the before node, and we can find the before node using the same integer index. In this case, because we don't want to find the index, but before the index, and to find the before the index we have index minus 1. And once we have find this element before the index 1, we need to point this next to this new node and what it was pointing before to this value. So we can do this like we have find the before, and the before is equal to before dot next. So it means that before this value we have assigned to the before, and then we have assigned the values accordingly. In this way, when we use a linked list and we add a value in the middle, a node in the middle, we don't need to move the values forward. And similarly, if we move some value node, then we don't have to backward, which was the problem in case of array-based implementation. So this is the same again with the remove. If you want to remove an element and a specific index, for example, the same element, if you want to remove the element at index 1, and first of all we check the index, and yeah, I have just commented the value yeah, for the index 0. You need to handle this yourself, but that will be not complicated because you just need to check the index. If index is equal to 0, then you just point your head from your first node to the next node. But here, yeah, we need to find out the before, and we also want to find out the node that we want to delete. And once similarly, we have if we want to find out delete this node, remove this node, it means we need to find the node before that, and we have to bypass this one. And we can do this bypass by finding a before and pointing the before dot next is equal to what was in the delete dot next, because the delete dot next was pointing to this element, and from here we can just point out that this before dot next should not have this element but the next element that was pointing by the delete element. Okay, and similarly, yeah, that's the same way that we done iterator interface in the array base, there is no much difference. Only difference is that instead of iterating through the index values, you can use this node.next to iterate to the next elements in your linked list implementation. And then we have a few other variants. That was the implementation that we looked before. It was a simple kind of a linked list implementation. There are two other variants. The first variant we call head and tail. In the normal variant, we only have if you look at here, in the list we only have the head that will be pointing to the start of your list. But if you want that, for some cases, if you want that, you can have, for example, in the DQ, where we can add elements at both ends. And if you want to implement a DQ data structure using a linked list technique, or if you want to do the queue, even the queue structure, because in the queue structure, you add element at the bottom, but you access element from the front. So it means that you need to access from both ends. So in that case, maybe we can have another element, another attribute with the name of tail. As it says, the problem with the simple implementation is that to add elements, we need to step through the whole list. So for example, if you want to add the element at the bottom, you have to go through the first. If you have 100 elements at the beginning and you want to add another element, like let's suppose at the index 101, then to add an element at the index 101, you first have to go through all the starting elements, starting from the 0 index until the end, to add at the end. But if you have this implementation, you have an address to the tail. Tail means the last node in your list. Then you can add the element simply by going through this, using this head and tail approach. So simply this head and tail approach, you have head and then you have a tail, which is holding the reference to the last element in the list. And we can also have a double linked list based implementation. What is the difference between double linked list and the simple one? Because here, in case of in the simple linked list, we have only the next, which is pointed to the next elements. So it means that we can also we can only access the elements in one direction, but we cannot access them in the backward direction. If you want to access the elements in the backward direction, we can have the double linked list, in which we have the node will have another attribute, previous, which will be pointing to the previous attributes or the nodes in that list. Okay. And the difference between linked versus array-based implementation, there are a few differences. We don't have to shuffle elements in remove and add it, because if you are using the linked list, you have already seen that when you add, you don't need to adjust the values. And there is no problem with the resizing and no waste of memories. But the problem is sometimes often this get method will be the slow, because in the array, you specify the index and you get the element immediately. But if you look at here, when you use the index element, at the you have to define your own get implementation, and you have to go through from the 0 until the index and access all the elements. For example, if you have same like as I said earlier, if you have 100 elements and if you want to access or the get element in the middle, either you are using the head and tail approach, you have to go from, even if you start from the bottom, you have to visit the last 50 or the first 50 element if you start from the head to get the element in the middle. But if you're using the the array-based implementation, the get will immediately return you the element at the specific location or the specific index. And so the Java library class provides us these different data structure implementation, array list and linked list and vector. Some of these are array-based. For example, array list is an array-based implementation. This linked list, it uses the double linked list. And the vector is again an array-based thread safe. So we have looked at these different implementation in the Java collection. So there was something about array-based and linked list-based data structures. The next form of the data structure implementation is tree-based data structure implementation. And the tree, as you already have been familiar, it's basically a collection of finite set of nodes. So for example, you have been familiar with the tree that you have nodes and you have branches and the sub-nodes like a parent and child tree. And so basically you have a tree is a collection of nodes and edges. What are the edges? Edges are this connection between one node and another node. And there are some rules. The most important rule is that all nodes, but the root node will have only one parent. So in this case, tree cannot have more than one parent. And that's only for the sub-nodes. And the node with no parents are called root of the node or root of the tree. And each node may have 0 or more than 1 children. So for example, here, the node A has 3 children, immediate children. But there might be the B has only 2, C has only 1. And K, L, and M, they don't have any children. And the nodes without any children, these are known as leaf nodes. And there are also some other concepts. For example, the path. The path is basically, if you have nodes N1, N2, and N3, so the edges and the nodes that link one node to another node, they form a path. So for example, in this case, suppose that N1 is the parent of N2, which is the parent of another node N3, and so on. In this case, the sequence of nodes between one node to another node is the path of that tree. And the length of it will be, for example, if you have 1, 2, 3, 4 nodes, and if you want to find the length of the path is basically the number of edges between those nodes are along that path. So if you have 4 nodes in a path, the length of that path will be the number of nodes minus 1. And also we have this concept of ancestor and descendant. Basically, the parents are known as the ancestors. So in this case, the A is the root node, so it is the ancestor of all the sub-nodes, and descendants are the children. So for example, all these other nodes are the descendants of the root node A in this case. So if we look at this example over here, so this should not be 1, this should be root A. Here, if you look at this example, the root of this tree is A, leaves are the nodes at the bottom, K, F, L, M, and H, I, and J, because these are the without the children. And then the height of the tree is equal to, and if you know about the height, it is basically the height of the tree is the length of the longest path. So you need to find the longest path, and then you need to find out the number of edges to find out the height. And similarly, we have another concept, the depth. The depth of our level of node n is the length of the path from the root to the n. So just to remember, the difference between height and the depth is that the height is measured from the leaves to the node, and the depth is measured from the root to the particular node. So if you go here, if we want to find out the height of the node B, here is the B, and height will be measured from its leaf to that node, and we will find the longest path that could take from the leaf to that node. So so in that case, height of the node B will be 2, and the depth or the level of the node B will be, here B is missing, so I will fix that, because the depth is measured from the node to the root. So in this case, if we measure the length from here to here, there is only one edge in between. So that's why we call the depth of the node is 1. And we use this kind of examples of tree data structure is there are different scenarios where we use tree to represent the information. So one such scenario is when you have this the file system. We have directories, folders, subfolders, and files which are connected in a tree structure. And then we also have syntax tree. So if you have a compiler and the compiler, you are passing your statements using a syntax tree. And then we have a specialized form of a binary tree. A binary tree is a tree in which each node may have maximum 2 children. So for example, if we look at here, is this a binary tree or not? A binary tree, what is a binary tree? Binary tree cannot have more than 2 children. In a binary tree, none of the nodes can have more than 2 children. So if we look at this tree, is it a binary tree or not? Why? D got 3 children. Okay, so it means that this is a tree, but not a binary tree. The restriction in a binary tree is that none of the nodes can have more than 2 children. And then we have a specialized form of a binary tree, which is called as binary search tree. A binary search tree have these properties. For each node x, the values of all the nodes in x left side are less than the value of x. Okay, what does it mean? It means that if you have these values 4, 2, 5, 1, and if you want to represent them in a tree, in a binary search tree, so for example, we start with the 4. The 4 is the root node, and then we take the next, which is 2. So this next value, we check if it is less than the parent, then it should go to the left side. And if it is higher than, then it go to the right side. So it says that for each node x, the values of all the nodes in the x left subtree are less than the value of x, and those values which are greater than the node, it will go to the right side. And in this case, we start 1, we go with here, we compare it. 4, 1 is less than 4, it means this should go to the left side. So we go to the next element, compare here, 2 is less than, 1 is less than 2, so this one should go to the left side. And if we got another value, for example, if we got value 3, we go here, 3 is less than 4, should go to the left side, and here it's a greater than. Okay, and this kind of tree which preserves these properties is known as a binary search tree. And the values it means that the values in binary search tree are automatically sorted. We will see how these are automatically sorted, because all the values on the left will be less than the node itself, and all the values on the right side will be greater than. Okay, so and all updates of the binary search tree must preserve the values, must preserve these properties. It means that if you make any changes, if you add or remove a node, so whenever you make some changes, these properties should not be violated. So it means that if you remove the value in a node, then the changes should be still, it should not affect the properties of a binary search tree. Now here we have some trees. On the left side, we have a simple binary tree. Why it's a simple binary tree? Because 7 is greater than, so it cannot be on the left side. It must be on the right side. On here if you see here, all the values on the left are less than the node itself. For example, here 4 is less, and all the values on the right are greater.
What if the balance is same? Like if you got 2 of them falling here.
Sorry?
What will happen if the balance is same?
Okay, normally in the binary search tree, we don't allow duplicates. Okay, Normally, you don't allow duplicates. If you allow duplicates, you can decide by yourself either the duplicate value should go to the left or the right. It doesn't matter, but you should be consistent. But in general, you don't have duplicate values in a binary search tree. And to implement this in Java, we have a class int binary search tree. And if we look at this class here, let me close. So in this we have one attribute, root, which is of type binary search tree, and this type is basically an inner class in which we have a value attribute, and then we have a left and right, which are just to maintain the pointer to the left child and the right child. And then we have in this int bst, we have the method add, contains, remove, and print. The add method, in the add method we check if the root is equal to null. It means that it's an empty tree. We assign the root, we create a new node, tree node, and assign it to the root. Otherwise, we call the root, the add method on this, the root element, which is of type bst. So it will call the add method in this bst class, and in this add method, we check the value. If the value is less than the node itself, then we go to the left side and check if the values, if the left node is empty, we add it to the left side. Otherwise, we call this method iteratively until we get an empty or the leaf on the left side. And if the value is greater, we go to the right side. And same happens if you are finding a value. We have a contains method which finds out a value in a tree and returns either true or false. If the value is found, it returns true, otherwise it will return a false. So, and to find the value n, we compare it with the root node, and if the value is less, we go to the left side, and we continue this until if we don't get any null value. If we get a left is equal to null, it means the value has not been found and we have reached to the last element, so we return false. We do not find a value. Otherwise, we keep on iterating and keep on looking at the values. And if the value is greater than, we go to the right side and we do the same. If we get to the null point, it means that we have not found the value and we return a false. Otherwise, we keep on looking. And if none of these false has been met, it means that we have found the values, and if we have found the values, in that case we will return true. Okay, so this is how we can implement a binary search tree. So that's the add description of just the add method, which I have now described already. So now here we have two examples. We have the same different elements, but they are in different orders. And if we want to add these elements to a binary search tree, we get these two different binary trees. However, one of these binary tree is not correct. Which one is not correct? Right one. Why? It's not. Which node has a problem? 16 is less than 19, so it should go. Okay, 16 is less than 19, so it cannot come to the right side. It must be on the at some other location or to the left side. And another thing important is that here we have an error in first figure. 16 is at a wrong position. And also, if another important thing to notice here is we have the same values in these two nodes, but if we change the order in which we add the elements, we get two different search trees. The structure of this tree is different than the structure of the other tree. And yeah, and usually we don't have a duplicate entries. So if you try to add a duplicate, it should be ignored in a binary search tree. The contains method we already have looked. And then, yeah, this is an example. If we look at, if you try to search for a 14, since we are looking at the search contains method iteratively, so we look at here in the first step. If it's less than, we go to this and do another step, compare again. Again, if it's a less, we go to this step and we go. Now in this case, the value is greater, 14 is greater than 12. So we go to the right side because the value is greater. And on this thing here, when we go to the contains method, remember the value of the node is 14 and the value we are searching for is also 14. So if I show you the contains method here, this condition 14 less than 14 false. We go to this next part, this one 14 greater than 14 false. So it means none of these, if the value is neither greater nor the less, that means the value is equal to the 14. In that case, we will return true, the value is found. So it means that we checked here, 1, 2, 3, and we checked here. And at the fourth attempt, we find the value of 14. And similarly, if you look at here, we are looking for the value 34. We check it here, less than. In the first step, we go to the left side. Here it's greater. We go to the right side. Here we check. 37 is greater than 32. No, 34 is greater than 32. So we go to the right side. However, on the right side, we have a no element. We have no node. It means that we get to a null value. So in that case, it will return a false. But we have to do 3 checks here. 1, 2, 3. Now the problem with this, imagine inserting values 1, 2, 3, and 4 in this order. So we're starting with the node value 1. We add 1, and then we have a value 2, which is greater than 1. So we go to the right side, and then we go to the another value 3, which is also greater than 1. We go to the right side 2, which is again greater 3. Although this is a tree, but it is not a balanced tree. We are just branching in one direction. So the problem with this kind of trees will be, if you add the numbers in this order, we do not get a branching tree or kind of a balanced tree, but a linear tree which is going only in one direction. All of the left subtrees are empty. And if you get this kind of tree, it means the tree is not balanced. And due to this not balanced tree, in the worst case, if we are looking for a value 4, we have to visit all these elements. Okay? It means the time complexity will be the worst case, will be the number of nodes in that tree. However, if we have added these elements in a balanced way, at each step we can skip half of the elements. Why we can skip half of the elements? Because at every step we compare the value, and if it is greater than or the less than, if it's less than, we remove the half part, we skip the right part, we just focus on the left part, and keep on doing that until we get the value. But in that case, since we have a tree branching in only one direction, not on the other direction, so we will not be able to get the benefit of faster search operation, because the binary search tree, it provides you with a faster search operation or faster get operation, which is normally a problem with the linked list, because in the linked list, if you want to get or look up for an element, you have to transfer all the elements from 1 to until that you get an element. So we can fix this problem by using the an advanced form of this binary search tree, which we call the balance tree, or the self-balancing tree. And the feature of this balance tree is that it keeps on trying that the height of each left tree and the height of each right subtree is equal or nearly equal. What it means that in the tree, the height of this tree and the right and the left should be either equal. For example, in this case, 1, 2, 1, 2, 1, 2, 1, 2. But here, if you see here, the difference is this has a 1 and the other one has 0. So, but still more or less equal or nearly equal. And from this, we get two kinds of balance tree. We have a balance tree if the height of the left and the right subtree from every node differs by 1 or by 1 or less than 1. So in this case, tree shown in the figure A is a balanced tree. But if you have you will get a perfectly balanced tree if the height and left and right subtrees are equal at every node. So it means that with the depth of n, when you have number of nodes here, the number of elements, if the depth is n, okay, in this case, what is n? 1 and 2. And then, and if you look at here, 2n plus 1, n is 2, plus 1 is equal to becomes 3, and 2 raised to power 3 becomes 8, and 8 minus 1 becomes 7. So if you have a perfectly balanced tree, when the number of elements are 7. If you have a less than 7, then it means that you don't have a perfectly balanced tree. And then we also have the print method in this binary search tree implementation, where you just simply, if left not is equal to null. Basically, there are different ways to visit or print the elements or nodes in a tree. The first one we have is in order visit. What does the in order visit means? That we go to the inner nodes first, and then we print the node itself. It will become more clear here. Tree traversal strategies. Basically, we have two kinds of tree traversal strategies. We can either visit or traverse a tree in the depth wise, and the depth wise means visit a tree as dependent as possible on each child node before going to the next sibling. And for this, we have three different forms: pre-order, in-order, and post-order. In the pre-order, we first visit the node itself and then go to its left subtree, and after visiting the left subtree, we go to the right subtree. We will see the examples and then it will become more clear. And in the in-order, we first visit the node itself, then go to the left side, and after that, we go to the right side. And in the post-order, we first visit the left subtree, then we visit the right subtree, and at the end, we visit the node itself. Okay? And what is the breadth first? In the breadth first, instead of going from root to the bottom or the leaves, we go in the horizontal direction. We first visit the nodes at the level 0, and then we go to the next level and keep on until that we get to the lowest level. So here, if you saw the pre-order, in the pre-order, we first visit the node, then we go to the left subtree and visit the nodes, and then after we have completed all, here we go to the right side. So if we follow this pre-order tree traversal, we visit the node 4, then we go to its left side, and in the left side we visit the node itself first. So we visit the 2, and then we go to its left side, we visit 1, and after that, since there are no on the left side, no on the right side, we go back and then visit the right side, and then we go back. Since we have already visited 4 and 2, and we already visited the left tree, so then we go to the right side, and So in this way, we will get the elements. And when we go to this node 6, once again, we will visit this node itself, and then we go to the left side. And completing after this left side, we will go to the right side. So this is the pre-order. In the pre-order, we visit the node itself first, and then we go to its left side. And after visiting the left side, at the end, we go to the right side. But if it's like in order, in means the root is, the node is in the middle. We first visit the left, then we go visit the node itself, and at the end, we visit the right. So visit left subtree, the node is in between, in the middle. That's why we call it in order. And then we go to the right subtree. And if you visit in this in order, you will get an ascending order, sorted list. Okay. So we start from the root, and we go to the left first, because it says that visit left subtree first. And at each node, we go first to the left side and visit. And then after completing this left order, we go to the right side. And then next is the post order. In the post order, we first visit left, and then visit right. And at the end, we will visit the node itself. Okay. And in the breadth first, as I said, instead of going downward to the leaves, we first visit on the top level, and then we visit the next level, and then so on until the last level. Okay, so these are the different ways that you can visit or traverse different nodes in a binary search tree or any other binary tree data structure. So this brings us to the end of today's lecture. So here are some recommended readings. So you can look at, I mean, it's hard to find out one book that covers all these details. But if you look at this book, and we have provided you with the reference of this book on the Moodle page as well. The problem with this book is that it's implemented in C, but the basic concepts are same. And also, I recommend that just Google the concepts that you have learned, and you will find some tutorials. And in the next lecture, we will read about the graph data structures and the different types of the graphs. Okay? Thank you very much.